Hello, and welcome to Astronomy 100. In this section, what we're going to do is begin a fairly long portion of the semester of the course where we're going to talk about stellar evolution. And the topic of stellar evolution is a fairly lengthy one because there's a lot of components to it that describe how stars are formed, how they live, how they produce their energy, and of course why they eventually die. So some of the key concepts that we're going to address are, first of all, where do the stars actually come from? And we'll talk about how we have discovered places in our galaxy that are the places where the stars form. Of course, then we'll talk about how stars form and why there are stars in the first place. What is it that is about our universe that makes stars possible? Then we'll talk about how stars create the light that they produce. It's a fascinating and a little bit of a complicated topic that describes how stars produce their light. Then what we're going to do is describe how stars and why stars ultimately die. You'll notice the quotes over the word or around the word die. Stars are not living creatures, so they don't actually live and die, but they do end their existence in a way that is similar to death. And then we'll talk about what do the stars become after that process of death has occurred. So to begin the topic of stellar evolution, let's actually look at the words stellar evolution themselves. Evolution simply means when something changes over a period of time. And in the case of stars, they go through some fairly dramatic changes throughout their entire existence. This picture here, or this illustration here on the right, is chronicling all of the things that will happen when it comes to the changes that our sun will experience throughout its entire existence. And of course, we'll talk about the details of all of these things individually. But just very briefly, you can see that the sun formed from a cloud. It became a very, very stable star for an enormous period of time, and currently we're experiencing that period of time that is the stability part of the evolution of the sun. And then in the future, the sun will become unstable, it'll change quite dramatically, and then of course it'll become an object that will essentially be the eternity of its existence. So what we're going to do in this section is describe how the sun has formed and will exist and change and then die. And then of course we'll talk about how other stars do this as well. Now speaking of other stars, let's return to the idea of categorizing the stars for just a minute. When it comes to the stars, if you recall in a previous video, we talked about how the spectral lines of a star will create patterns, and stars have certain features to their patterns that allow us to put them into categories. And we call this the spectral classification sequence. Well, there's one final category that goes with this that is a good segue into the topic of stellar evolution, and it's called luminosity class. Now you'll notice this Hertzsprung-Russell diagram here on the left has the same features that we saw in the previous video, but what I have now added to it are some names up here on the upper, I guess the upper right part of the diagram. And you'll notice that the names all have features to the words that sound like they're related to size. We have supergiants, we have luminous giants, we have giants, subgiants, and then we have the dwarves. Now in our universe, when it comes to stars of different types, we can put them into another category called luminosity class. And let me bring up the abbreviations. Luminosity class has to do with some of the features of the star itself, but in many ways the luminosity class is a product of the size of the star as well as how the star is producing energy and where it is in its evolutionary sequence. We'll talk more about that in just a second. So let's first start with the abbreviations. You'll notice these are all Roman numerals. We have stars that are supergiants, luminous giants, which are Roman numeral 2, giants that are Roman numeral 3, Roman numeral 4, subgiants, and then of course Roman numeral 5, which are the dwarfs. Now, the names are a little bit strange because these are names that go back about a century, and so they're not entirely politically correct, I guess you could say. But in many ways, what it's referring to is the size of the star, how much energy it's producing, but most importantly, where it is in its evolutionary sequence. And you'll notice that they're located in different parts of the HR diagram. The supergiants are up here, luminous giants over here, etc. And we'll start to weave this into our topic of stellar evolution as we go. One of the things that's important to notice is that the sun, located right here on the HR diagram, makes the sun in the luminosity class category of dwarf. So our sun is what is called a main sequence dwarf, and we'll talk more about what the term main sequence means in just a second. And some things that are important to know: stars, as they form and they live and they die, they change their luminosity class. So the sun is currently a dwarf, and in the future the sun will be a subgiant, and then it will be a giant. Some stars will go all the way up to this category of supergiants when it comes to their luminosity class. And we'll talk in future videos which ones make it however far they do and why that occurs. So the stars change their luminosity class as they change the various characteristics of them and all the features that go with them. Another thing that's important to notice is the numbers of each of these categories. Not necessarily Roman numerals in this case, but what I mean is the quantity. Notice that there are very, very few subgiants, stars that would be luminosity class, Roman numeral 1. And if we go all the way down to dwarf, you'll notice that the overwhelming majority of the stars on the HR diagram are what we would consider dwarfs. So in our universe, there is an enormous number of dwarfs and very, very few supergiants. And we'll again find out why this is. But just some statistics: about 90% of all stars in our universe would be considered dwarfs. So even though the word dwarf sounds like the sun is a very small star, comparatively speaking, it is of course a very small star compared to how big stars can be. The sun is very big compared to you and me, but some stars in our universe can be up to 1,000 times as big as the sun, and so in that respect it makes the sun a dwarf, even though to you and I it would be very large. So it is very common to have dwarfs in our universe, and very, very rare to find supergiants. And we'll find out why that is, of course, in a little bit. So when it comes to the HR diagram, there are other things we can do with it that I want to sort of transition to. If you look at all the dots, it can be a little confusing. You can see that they're all over the place. Remember, each dot represents an actual star. Don't forget that the left side is luminosity, the right side is absolute magnitude, across the top is a change in the surface temperature, and across the bottom is the spectral type. Even though these dots that are representing stars are scattered all over this diagram, you can actually see that they can be sort of cordoned off into three main groups. There's a group that's the upper right up here, and you'll notice that a lot of these stars up and down the middle act as if they're in one group, and then down here there's a group as well. And the reason why they group together like that has to do with the fact that they have similar characteristics. So all of the stars up here are doing something that is very similar. All the stars here have something in common that they're doing, and all of the stars down here have something in common as well. What we're eventually going to find out is it has to do with how a star changes its characteristics over its entire lifetime. And we're going to talk about the individual changes that occur, and we'll go into that into sort of exacting detail as we get to it. But let's sort of summarize a couple of ideas to start with. For instance, all of the stars that run up and down the middle of the diagram, these are all stars that have one particular set of characteristics in common. And we're going to call this the main sequence of the HR diagram. This is a very, very important term, the idea that these stars are what are called main sequence stars. And the reason why is because this part of the HR diagram is called the main sequence. So any star that is on this part of the diagram is a main sequence star. And so you're going to hear the term main sequence over and over again in these coming videos because it's a very important idea. For instance, the sun is a main sequence star today, but in the future, the sun is going to move and leave the main sequence, and it'll do some other things that are different related to its evolutionary sequence. A lot of the stars up here used to be on the main sequence, but are no longer. So this is called the main sequence. And let's start off with the first thing that they have in common is that all main sequence stars are stars that are normal stars that have finished the formation process and are actively producing energy, and they're going through their life sequence, and they haven't reached the end of their life. So often it's convenient to make an analogy to humans. Let me give you a human example. When you're born, you go through a lot of physical changes, and you grow and you change your characteristics until you become stable. You become an adult, you stop growing taller, your feet stop growing bigger, your clothes size stay the same, and you're in a period of time in your lifetime where you're physically not changing a whole lot. And then towards the end of your life, you go through some dramatic changes based on if your health is declining. Usually people at the end of their lives go through some physical changes that are quite dramatic. Main sequence stars are the equivalent of human adults. So they've finished the formation process, they're going through their day-to-day existence, and then someday in the future they're going to stop being normal stars, and they will start to very quickly head towards death. So main sequence stars are like human adults that are older than 18, let's say, and younger than, let's just say elderly. We don't want to offend anybody. So somebody who would be elderly would be considered somebody who's starting to go through some changes at the end of their life. Now, this group up here, these are stars that we're going to put into air quotes, of course, or the quotes here. These are stars that are dying. And what we mean by that, since stars are not living things, in this case, these would be the equivalent to adults that are towards the end of their lives. Maybe they're sick and they're going through some changes. Maybe they're terminally ill with an illness of some sort where their days are numbered. So a star that is quote unquote dying is a star that is rapidly changing its physical characteristics, and it is getting close to the end of its existence. It's reaching the end of its evolutionary sequence. Now these stars down here, these are stars that have completely finished their evolutionary sequence. In other words, they have gone through their formation, they have been on the main sequence for a period of time, they then moved up to this portion of the HR diagram, changing the characteristics to become up there, and then they've ended up down here. Remember, every time you move on the HR diagram, you're changing something physically about the star. Some physical characteristic is changing. If a star moves simply upwards, vertically upwards, then it's becoming more luminous. If a star moves to the left, then it's becoming hotter. If a star is moving diagonally, then it's a combination of some of these characteristics. Remember that each of these sides of the HR diagram has a physical characteristic attached to it. So the moral of the story is that when stars go through their lifespan, their evolutionary lifetime, if you will, they're going to change their physical characteristics. And as they do that, they're going to evolve, meaning change over time, and it altogether creates a lifespan or a life sequence that will be the lifetime of the star. There was a time when the sun didn't exist, the sun formed, the sun began to produce energy, the sun is going through its normal, everyday period of its life. That's what we're benefiting from right now. And then in the future, the sun is going to change very rapidly and then end its ability to produce energy as if it has died. So when we say stellar evolution, we're really describing this period of time that a star is in existence and how it's changing over that period of time. Now, what we're going to talk about is we're going to start off by describing where do the stars form, and then we'll talk about how they form, and then we'll transition to how they produce their energy, why we call them stars, and what it is that a star is doing that makes it a star. And then we'll talk about how they someday lose the ability to continue to make their energy, and then they will eventually at some point become something very different, as if they had died. So we'll save that for the next video. We're running just a little bit short on time, so we'll pick it up in the next one. I hope you'll join me.